Friends, let us start with the second type of boundary condition, that is penalty approach method. Consider a spring of large stiffness C is introduced into the model. One end of the spring it is displaced by an amount of A1. Let the displacement Q1 along the degree of freedom approximately equal to A1. That is what the boundary condition Q1 which is equals to A1. Due to the relatively small resistance offered by the structure. So we have a structure. So one end of the structure, it is modeled by a large spring having a stiffness of C. Like the structure having a node 1, at node 1 the displacement is Q1. So this spring, it undergoes an extension of A1. So the net extension of the spring, which is given as Q1 minus A1, that gives the extension of the spring. Now, the strain energy in the spring, which is given as U is equals to half times of K into X square, where K is the stiffness, X is deflection of the spring, which is equals to half times of. So, stiffness, which is defined as a C, and X is nothing but deflection of the spring, which is the difference in Q1 minus A1 whole square. So therefore, total potential energy phi, which is equals to half times of Q transpose K into Q plus half times of C into Q1 minus A1 whole square. So this is the strain energy for the structure, and it is the strain energy for the spring, which we consider. Minus work potential is Q transpose into F. This is the total potential energy for the structure as well as the modeled spring. Now we have to minimize the potential energy functional. So for potential energy to be minimum, so partial derivative of phi by dou times of qi. So you have to derivative, or you have to take a derivative of the potential energy functional with respect to the variable. So here the variable is q. So qi, where I stands for 1, 2, 3 up to n. So when you do the partial differentiation of this with respect to the variable, so it will result a set of equations. Those set of equations, it is represented in matrix form. So it will result a matrix. So that matrix, it is in the format of equilibrium equation, that is K into Q, which is equals to F. In the equilibrium equation, so we can see a little modification. So the modification is there is a addition of the C to the elements of the stiffness matrix, as well as one more addition, that is C into A1, which is for the force vector, where the C is nothing but the maximum of K of ij into 10 to the power of 4. So that is the maximum value which is present in the stiffness matrix multiplied by 10 to the power of 4, where A1 is nothing but the known displacement. And you can find out the reaction force at node 1. So at this particular point, you can find out the reaction. So which is given as R1, which is equals to minus C into Q1 minus A1. So C is the stiffness of the spring, Q1 is the nodal displacement at node 1, and A1 is the displacement of the spring. So this is the concept of penalty approach method. Now let us start with a few examples of applying the penalty approach method. So simple numericals. So the first problem, a compound bar is loaded as shown in figure. So Young's modulus for the steel, it is 200 GPa. Young's modulus of copper, it is 100 GPa. Using penalty approach method of boundary condition, find nodal displacement, stresses in each element, and reactions at supports. So here we have a bar. So it is the bar. So one bar it is made up of a steel material, the other bar it is made up of copper material. Both it will have the different cross section area. So it will have a diameter of 60 mm, it will have a diameter of 40 mm. Length is 800, 500 mm. So element numbers it is already mentioned. So this is the element 1, this is the element 2. So no modification in element numbers. And the load is applied at exactly center of the element. Now the diameter is here given. So you convert the areas. So area of the elements A1 is pi d square by 4. So pi into 60 square divided by 4 will get the area. Similarly, you find out area of the second element. So pi d2 square by 4. So pi into 40 square divided by 4 you will get the second area. Now go for the step 1. The step 1 is you have to write down the finite element model. So you have to represent the given bar element into the finite element model. So the first thing is you have to do the numbering of the elements. Already in the problem, they mentioned the element numbers. Now the second step is you have to locate the nodes. In order to locate the nodes, we have to check the direction of the coordinate axis. So the direction of the coordinate axis, it is along this direction. So numbering of the nodes, it has to start from left hand side to right hand side. So you have to model this by 3 nodes. So here you have to place one node, here you have to place one node, here you have to place one node. So it is end of the bar. Here also it is end of the bar. Here the cross section area it get changes. So you have to introduce one node, or a load is applying at the middle of this. So you have to introduce one node. So this it has to be modeled by 3 nodes. 1, 2, 3. And numbering it has to start from left hand side to right hand side. So it is represented over here. So this is element 1, this is element 2. So numbering of the nodes 1, 2, 3. Now like at node 1 the displacement is q1, at node 2 the displacement is q2, at node 3 the displacement is q3. Go to the second step. We have to determine the elemental stiffness matrix for each elements. So we have two elements. So for element 1, so K1 which is given as A1 E1 L1 1 minus 1 minus 1 1. So substitute the value of A1. So it is 2827.43 into E. E is separate. So the element one is a steel. So you have to take 200 GPa. So 2 into 10 to the power of 5 divided by length of the element. So it is 800. So you do the simplification of this, we'll get 7.07 into 10 to the power of 5. I will keep 10 to the power of 5 outside and I will send 7.07 inside. So we'll get minus 7, sorry, this is positive, plus 7.07 minus 7.07 minus 7.07, 7.0. So there is some mistake. So it is all are 7.07. So plus 7.07 minus 7.07 minus 7.07, 7.07. You do the numbering as 1, 2, 1, 2 because for element 1, the stiffness matrix is consisting of node numbers 1, 2. You represent here 1, 2, 1, 2. Similarly, you find out the stiffness matrix for second element K2, which is equals to A2, E2, L2. So 1 minus 1 minus 1, 1. You substitute the values of this. So A2 is 1256.63 into the value of E2. So it is 100 GPa. So you'll get 1 into 10 to the power of 5. L2 is 500 mm. 1 minus 1 minus 1, 1. So after simplification of this, we'll get 2.513 into 10 to the power of 5. I already removed 10 to the power of 5 outside in the first element. The same number you have to remove here also. So remove 10 to the power of 5 into 2.513 minus 2.513 minus 2.513, 2.513. So element 2, it consisting of the node numbers 2, 3, represent here 2, 3, 2, 3. So this it will help to find out the global stiffness matrix. Now you find out the global stiffness matrix, that is K, which is equals to the sum of the individual stiffness matrices. We have only two elements, so it is the sum of K1 plus K2. Therefore, K is equals to, in both the elements, we remove 10 to the power of 5, 10 to the power of 5. So here also you remove 10 to the power of 5. So you write the matrix. So since we have three nodes, so the global stiffness matrix, it will be 3 cross 3. So represent 1, 2, 3, 1, 2, 3. Now you have to find out the elements which are present in the global stiffness matrix. So here the element is K11, here the element is K12, here the element is K13. So in order to find out K11 element, so it is 1 cross 1. So it represents K11. So here it is 1 cross 2 or 2 cross 1. So it is K12. 3 cross 1 or 1 cross 3. That is K times of 1, 3. Now go for 1 cross 1. So it is K11. You check it over here. Here we have 1 cross 1. It is minus 7.07. Here we don't have. So write minus 7.07 as K11 element. Again go to 2 cross 1. So 2 cross 1, here we have minus 7.07. Here we don't have 2 cross 1. So you write as it is minus 7.07. Again go for 3 cross 1. So 3 cross 1, here it is not there. Here also it is not there. You directly enter it as a 0. Now you write the row elements as a column element because of symmetry. Now you go for this element, so it is 2 cross 2. So 2 cross 2, so here it is 7.07. Again here also we have 2 cross 2, it is 2.513. You just add up these two. So 2.513, 7.06, we get 9.583. Similarly, you go for 3 cross 2. So 3 cross 2, so we have minus 2.513, you write as it is. Now you write the second row as a second column. Finally, you find out the 3 cross 3. So 3 cross 3 is 2.513. So this is the way of finding the global stiffness matrix. Now determine the global force vector, that is F, which is equals to F1, F2, F3. Similarly, determine the global displacement vector Q, which is equals to Q1, Q2, Q3. So we have only three nodal displacements. Now you write down the equilibrium equation, which is represented as K into Q, which is equals to F. So this is the value of K. This is the value of Q, which is equals to the force. So K into Q, which is equals to F. So F1, so load at node 1 is 0, load at node 2. So it is 100 into 10 to the power of 3 Newton, and load at node 3 is 0. So no load is acting at that particular point. Now the next step is you have to apply the boundary condition. So as we discussed in previous video, we used elimination method approach. So in elimination method approach, wherever the non-boundary condition is there, the corresponding rows and columns are eliminated. But in penalty method, no elimination of rows and columns. For the given problem, the fixed supports are at the nodes 1 and 3. So in the problem, we have a fixed supports at node 1 as well as at node 3. So in penalty method of boundary condition, these fixed supports are modeled as a spring having a large stiffness of C. The value of C taken as C is equals to maximum of K of Ij into 10 to the power of 1. Since the supports are located at nodes 1 and 3, the coefficients of stiffness matrix with respect to 1 and 3, that is K11 and K33, are added up with the C value. So that is what the penalty approach method. So I explained already. So after applying the boundary conditions and after minimizing the potential energy, so the resulting equation, there we can see the addition of C. Now you have to add the C to the corresponding noun supports, that is 1 and 3. Now let us find out what is the value of C. So C is maximum of K of Ij into 10 to the power of 4. So C is equals to maximum of K of Ij into 10 to the power of 4, which is equals to, you have to find out the maximum value of K of Ij. So in the global stiffness matrix, so the maximum value when you observe it, so it is 9.583 into 10 to the power of 5. That is what the maximum value in this stiffness matrix. So it is 9.583 into 10 to the power of 5 into 10 to the power of 1. So when you add up this, so we'll get 9.583. So 5 plus 4, it is 10 to the power of 9. Now this is what the value of C. Now this C, it has to be added to the equilibrium equation. Now there is a modification. So you have to add the value of C to the coefficients of the stiffness matrix K11 and K33. That is, so here you have to add up, and here also you have to add up. So when you add those two elements, so the equilibrium equation, it will modify. So when you add this, so here you will get this term, here also you will get this term, which is equals to, even in the forces there is a modification. So F1, it is modified as F1 plus C times of A1. F2, it is modified as F2 plus C times of A2. F3, it is modified as F3 plus C times of A3. So load at node 1 is 0 plus C, you know. So it is 9.583 into 10 to the power of 9 multiplied by A1. A1 is the known displacement value at the node 1. When you come to the diagram, so here we don't have any known displacement. Here it is fixed, it is not allowed to move any deformation. So here the displacement is 0. That is the known displacement value is 0. So the value of A1 also, it becomes 0. So totally it becomes 0. Again F2 plus C times of A2. F2, you know, it is 100 10 to the power of 3. A2 also it is 0. So you will get 0. Similarly, the C times of A3. So A1, A2, A3. So none of the nodes it is allowed to move for a known displacement. So all the terms it becomes equal to 0. Now you solve this matrix, 3 cross 3 matrix, use a calculator. So once you solve this, directly we'll get the nodal displacement. The value of Q1 7.68 into 10 to the power of minus 6 mm. The value of Q2 0.104 mm, and the value of Q3 2.736 into 10 to the power of minus 6 mm. So that is what the way of finding the nodal displacement for the given problem. Now you find out the stresses. So for element 1, the stress which is given as sigma 1, which is equals to EBQ. So E, again B is nothing but 1 by LE minus 1 1 into Q. For element 1, the nodal displacements are Q1 Q2. You substitute for this. So E is 2 into 10 to the power of 5 into 1 by LE. Length of the element, it is 800 minus 1 1 into Q1 Q2. You substitute the value of Q1 Q2. You expand this, you will get a value of stress, that is 26.09 Newton per mm square for element 1. Similarly, for element 2, sigma 2 is equals to EBQ, which is equals to E2. So 1 into 10 to the power of 5, B 1 by LE. So it is 500 minus 1 1 into Q. For element 2, the nodal displacements are Q2, Q3. So Q2 is 0.104 and Q3 is 2.736 into 10 to the power of minus 6. You expand this, we'll get a value of minus 20.8 Newton per mm square. So this is the way of finding the stresses. Now the last one is we have to find out the reactions. So we have two supports. So one will get a reaction at node 1 and one more is will get a reaction at node 3, not 2. So it is node 3. So therefore R1, which is equals to minus C into Q1 minus A1. Anyhow A1 it is 0. So minus C into Q1. So C, you know, value, the Q1 is 7.68 into 10 to the power minus 6. Substitute this, we'll get minus 73597.44 Newton. That is 73.5 kilonewton. Similarly, you find out the reaction at node 3, that is R3, which is equals to minus C into Q3 minus A3, which is equals to minus C into Q3, which is equals to 26219.088 Newton. That is 26.219 kilo Newton. Now let us start with one more problem. A stepped bar as shown in figure using penalty method and elimination method, find the nodal displacement, reactions at support and stresses in each element. So take E is equals to 120 GPa. So here the problem is a stepped bar. So material it remains same. So here this is one stepped bar and this is one stepped bar. Here he has taken this as element 1, this is the element 2. The diameter of this is 60 mm, the diameter of this is 40 mm. Load is applied at the center, so it is 500 kilonewton. Length of this it is 600 mm, length of this it is 500 mm. But so when you see here, there is a gap. So the gap, the distance of that it is 0.1 mm. That means so at this free end of the bar, it is allowed to have a displacement of 0.1 mm. Now we'll solve the problem. So go for step 1. So represent the finite element model. Already element numbers it is predefined. So you see the direction of x, it is in this direction. You do the numbering of the nodes from left hand side to right hand side. So here you will get node 1, here you will get node 2, here you will get node 3. Represent this. So it is element 1. From here it is element 2. So node 1, node 2, node 3. Let the displacement at node 1 is q1, the displacement at node 2 is q2, the displacement at node 3 is q3. Go to the second step. Determine the elemental stiffness matrix. We have two elements. So find out the stiffness matrix for element 1 and element 2. So take for the first element K1, which is equals to A1 E1 L1 1 minus 1 minus 1 1. The value of A1, so it is pi d square by 4. So pi into 60 square divided by 4 into the E value. So it is 120 GPa. So 120 into 10 to the power of 3 Newton per mm square divided by 600. So you do the simplification of this, you'll get 5.655 into 10 to the power of 5. You remove 10 to the power of 5 outside and send the term inside. So you'll get 5.655 minus 5.655 minus 5.655, 5.655. Since the element is consisting of the node numbers 1, 2, you represent here 1, 2, 1, 2. You find out the stiffness matrix for element 2, K2, which is equals to A2, E2, L2, 1 minus 1 minus 1, 1, which is equals to. So area 2, it is 40 mm. So pi d square by 4. So pi into 40 square by 4 into Young's modulus 120 in 10 to the power of 3 divided by length of the element, it is 500. So if we do this, we'll get 3.016 into 10 to the power of 5. So I already removed 10 to the power of 5 in element 1. So you have to remove the same number and the remaining term you send it inside. So you'll get 3.016 minus 3.016 minus 3.016, 3.016. So for element 2, the node numbers are 2, 3. You represent here 2, 3, 2, 3. Now determine the global stiffness matrix, that is K, which is equals to the sum of the individual stiffness matrices. So therefore K, which is equals to, so already in element 1 and element 2 I remove 10 to the power of 5, you keep 10 to the power of 5 outside into the global stiffness matrix. We have three nodes, so the size of the stiffness matrix will get 3 cross 3. So represent 1, 2, 3, 1, 2, 3. Now I have to write the numbers or the coefficients of the stiffness matrix. So here the term is K11. So go for 1 cross 1. So 1 cross 1. So here we have 5.655. Here we don't have 1 cross 1. You write that number 5.655. Go to 2 cross 1. So 2 cross 1, it is minus 5.655. Here we don't have 2 cross 1. So write this number over here. 3 cross 1. So we don't have 3 cross 1 here. Here also we don't have. You write it as a 0 number. Now you write the row as a column because of this property of the stiffness matrix. Now you go for this. So it is 2 cross 2. 2 cross 2, we have 5.655. Here also we have 2 cross 2, 3.016. So you just add 3.016 with 5.655. So we'll get 8.671. Now you go for 3 cross 2. Here we don't have 3 cross 2. Here we have 3 cross 2. So it is minus 3.016. You write here. Now you write the second row as the second column. Now the last term is we have 3 cross 3. So here we don't have 3 cross 3. So here we have 3 cross 3, that is 3.016. You write here. So that is the way of finding the global stiffness matrix. Now you go for step 3. So write down the equilibrium equation K into Q, which is equals to F. So this is the stiffness, global stiffness matrix, global nodal displacement and global nodal forces F1, F2. Now you apply the boundary condition. So by using penalty method of boundary condition, the first thing is you have to find out the value of C. C is maximum of K of ij into 10 to the power of 4, which is equals to, in the stiffness matrix, you have to find out the maximum value. In this, the maximum value is 8.671 into 10 to the power of 5. Don't forget to add this. Okay, multiply this. So 8.671 into 10 to the power of 5 into 10 to the power of 4 will get 10 to the power of 9. Now, in the problem, so the fixed supports. So node 1 it will have a fixed support and node 3 it will have a fixed support. Now you have to add the value of C to the corresponding stiffness coefficients. So you have to add the value of C to A11 as well as for K33. So you just add 5.655 into 10 to the power of 5 plus 8.671 into 10 to the power of 9. Add it and you remove 10 to the power of 5 outside and you write the remaining term here. Similarly, 3.016 into 10 to the power of 5 plus 8.671 into 10 to the power of 9. Add these two, remove 10 to the power of 5 and write the remaining term over. So here the stiffness matrix it gets modified and you write down Q1, Q2, Q3. Similarly, the force also get modified. So F1 it is written as F1 plus C times of A1. F2 it is written as F2 plus C times of A2. F3 it is written as F3 plus C times of A3. So load at node 1 it is 0. Load at node 2 is 500 kilonewton. Load at node 3 is 0 kilonewton. So it is 0, 510 to the power of 3, 0 plus C times of A1. C is now 8.671 into 10 to the power of 9 into A1. A1 is the known boundary known displacement at node 1. So here the node 1 it is not allowed to move any displacement. So the value of A1 is 0. So you'll get final answer is 0. Come to the load 2 at node 2 F2 plus C times of A2. Here also the node 2 it is not allowed to move any displacement. So the value of A2 is 0. So totally the C into A2 it becomes 0. We'll get only F2. F2 is 500 into 10 to the power of 3. Come to the node 3. The value of F3 is 0 plus C. The value of C is 8.671 into 10 to the power of 9 into A3. When you see the diagram, the node 3 it is allowed to move for an amount of displacement that is 0.1 mm. So this 0.1 mm is the value of A3. So C 8.671 into 10 to the power of 9 into 0.1. That gives the value of C into A3. So finally you will get 8.671 into 10 to the power of 8. So this is the modification of the load vector. Now you have to solve this matrix. Use the calculator and solve it. Okay. So solve for nodal displacement, stresses and reactions. So by solving this matrix, we'll get nodal displacements. That is Q1 which is equals to 3.99 into 10 to the power of minus 5 mm, Q2 0.6121 mm, and Q3 it is 0.0995 mm. So this is the way of solving the nodal displacement. So go for finding the stresses. So for finding the stresses for element 1, sigma 1, which is equals to EBQ, so which is equals to E, it is 120 10 to the power of 3. B is the strain displacement matrix, which is given as 1 by LE minus 1 1 into Q. For element 1, the nodal displacements are Q1, Q2. We expand this, we get 122.418 megapascal. Similarly, for element 2, sigma 2 is equals to EBQ. So E, it remains same, 120 10 to the power of 3 into B is 1 by LE minus 1 1, and Q for element 2 it is Q2, Q3. So expand this, we'll get 122.92 MPa. Now the last one is we have to find out the reactions. So we have two fixed supports, that is node 1 and node 3. So node 1, that is a reaction R1, which is equals to minus C into Q1 minus A1. Anyhow A1 is 0, so I will write directly it as minus C into Q1. So which is equals to C, you know, the value of Q1 also it is calculated. Substitute this, multiply it, we'll get minus 34.6 kilonewton. Similarly, reaction at node 3 R3, which is equals to minus C into Q3 minus A3. Here A3 is a known value. So minus C multiplied by Q3 nodal displacement minus, so the value of A3. So node 3, it is allowed for 0.1 mm. So 0.1, you solve this, you will get 433.35 kilonewton. So this is the way of solving the bar problems by using penalty method approach. For more problems, you can refer this book. So I have solved so many examples. So please refer this book. Thank you.